In the previous classes, we have studied that whenever a organic reaction takes place, there will be a breaking of an old bond and formation of a new bond. That is, whenever any chemical reaction takes place, a bond breaks and a new bond forms. How will this happen? How does a bond break? A covalent bond is formed due to equal sharing of electrons. And when a bond breaks, it may break in two ways. One is known as heterolytic cleavage or heterolysis, and the other one is homolytic cleavage or homolysis. What do you mean by heterolysis? What do you mean by homolysis? Heterolytic cleavage. Heterolytic cleavage of a covalent bond can also be considered as unequal breaking of the bond. Now, let us consider an example of CH3Br. In the case of CH3Br, there is a covalent bond between the carbon atom and the bromine atom. That is, there is a shared pair of electron lying between carbon and bromine. And when the bond between carbon and bromine breaks, it undergoes heterolytic cleavage, that is, unequal breaking of the bond. Even though the electron pair is between carbon and bromine, whenever the bond breaks, both the electron pair will move along with bromine. Even though it's a shared pair of electron, whenever the bond breaks, the shared pair will go with one of the leaving fragment. That is, there is unequal breaking of the bond, and this leads to the formation of a carbon carrying a positive charge and bromine carrying a negative charge. The species which takes away the pair of electrons will carry a negative charge, and the species which gives electron will carry a positive charge. In this case, carbon is having a positive charge, and therefore it is known as carbocation, and bromine is having a negative charge and it is known as anions. That is, a species carrying a positive charge is called a cation, and a species carrying a negative charge is known as an anion. Therefore, whenever heterolytic cleavage takes place, it leads to the formation of cation and an anion. And in this case, CH3 plus is known as methyl cation. And these carbocations in general may be a primary carbocation, a secondary carbocation, or a tertiary carbocation. What do you mean by a primary carbocation? If the carbon carrying the positive charge, or if the carbon cation is attached to one other carbon atom, then it is known as a primary carbocation. That is, you have a carbon which is positively charged, and if this carbon is attached to one other carbon atom, as in this case, it becomes a primary carbocation. A secondary carbocation is one in which the carbon carrying the positive charge is attached to two other carbon atoms. That is, you have a carbon carrying a positive charge, that is, you have a carbocation, and if it is attached to two other carbon atoms, then it becomes secondary carbocation. Similarly, if the carbon carrying the positive charge is attached to 3 other carbon atoms, then it becomes a tertiary carbocation. That is, you have a carbon carrying a positive charge, and if it is attached to 3 other carbon atoms, as in this case, then it becomes a tertiary carbocation. Remember, the methyl carbocation, primary or secondary or tertiary carbocations all have trigonal planar structure, and the carbon carrying the positive charge is sp2 hybridized. All of these carbocations have sp2 hybridized carbon, that is, the carbon carrying the positive charge is sp2 hybridized and it has a trigonal planar structure. The order of stability of carbocations is methyl cation is less stable when compared to a primary carbocation compared to secondary carbocation when compared to tertiary carbocation. That is, tertiary carbocations are more stable when compared to a secondary carbocation when compared to a primary carbocation when compared to methyl cation. Heterolytic cleavage can also give a species in which the carbon atom may carry a negative charge. That is, let us assume you have a CH3 group to which a species Z is attached. Now, the bond between this carbon and Z will undergo heterolytic cleavage, wherein both the shared pair of electrons will move along with the CH3 group, and in this case the CH3 group will carry a negative charge and the other species Z will carry a positive charge. In this case, the carbon is carrying a negative charge and it is known as carboanion. Even in the case of carboanions, they may be primary carboanion, secondary carboanion and tertiary carboanion, depending upon the number of carbon atoms to which the C minus carbon atom is attached. If the carboanion is attached to one other carbon atom, then it is known as primary carboanion. If the C minus, that is carbon carrying the negative charge, is attached to 2 other carbon atoms, it is known as secondary carboanion. And if C minus, that is carbon carrying the negative charge, is attached to 3 other carbon atoms, that is known as tertiary carboanions. The organic reactions which takes place through the heterolytic cleavage are known as ionic or heteropolar or just polar reactions. Homolytic cleavage. The second way in which the covalent bond breaks is through homolytic cleavage, or it can also be considered as equal breaking of the bond. Now, let us assume a covalent bond which is formed due to equal sharing of electrons. In the case of homolytic cleavage, when a bond breaks, both the living groups will take their shared pair of electrons. Whereas in the case of heterolytic cleavage, both the shared pair of electrons will go with one of the leaving group, whereas in the case of homolytic cleavage there is equal breaking of the bond. That is, the shared pair of electrons will move with both the leaving groups. One electron will move with one of the leaving group and the other electron will move with the other leaving group. Now let us take a simple example, Rx. Here you have a shared pair of electron between R and X. Let us assume that the bond between R and X undergoes homolytic cleavage. In this case, one electron will move along with R and the other electron will move along with X. And if you observe here, I have mentioned the movement of single electron by a half-headed arrow. The movement of single electron is always indicated by a half-headed arrow, and the movement of a pair of electrons is always indicated by, as we have studied in the previous case, by a full-headed arrow. The movement of single electron is always represented by half-headed arrow. In this case, this electron will move with R and this electron will move with X, and this leads to the formation of free radicals. That is, whenever a covalent bond breaks by homolytic cleavage, then it leads to the formation of free radicals. Even free radicals are very reactive species. Free radicals are also classified as primary, secondary and tertiary free radicals. And coming to the order of stability of these free radicals, a methyl free radical is less stable when compared to a ethyl free radical. Here, the free radical is a primary free radical, which is less stable when compared to isopropyl free radical. In this case, it's a secondary free radical, which is less stable when compared to tertiary butyl free radical, which is a tertiary free radical. The organic reactions which proceed through homolytic fission are known as free radical or homopolar or non-polar reactions. In organic chemistry, we often come across nucleophiles and electrophile. What do you mean by a nucleophile and what do you mean by an electrophile? As the name suggests, nucleophile. Nucleophile means nucleus loving. That is, nucleophiles bring along with them a pair of electrons. That is, nucleophiles are electron-rich species and they attack the site where there is deficiency of electrons. Some of the examples of nucleophiles are negatively charged species like OH-, CN-, carboanions. These are all negatively charged nucleophiles having a pair of electrons. Even neutral species like H2O, R3N, R2NH are also nucleophiles because they have an excess lone pair of electrons, and these nucleophiles are electron rich and they attack the site where there is a deficiency of electrons, and such reactions are called nucleophilic reactions. On the other hand, electrophiles, as the name suggests, electron phile, loving. That is, these electrophiles take away with them the electron pairs. These are electron deficient species and attack this site which is rich with electrons. And the reaction which takes place through electrophiles are known as electrophilic reactions. Some of the examples of electrophiles are positively charged species like carbocations, neutral molecules having functional groups like CO, carbonyl group, and R3CX, that is alkyl halides, are some of the examples of electrophiles. Using curved arrow notation, show the formation of reactive intermediates when the following covalent bond undergo heterolytic cleavage. We all know that heterolytic cleavage is nothing but unequal breaking of a covalent bond, wherein both the electrons will go along with one of the leaving group, and the movement of a pair of electrons is always indicated by a curved arrow. Now we will take the first example, CH3, yes, CH3. Now it has been mentioned that the bond undergoes heterolytic cleavage, and in this case, when the bond between carbon and sulfur undergo heterolytic cleavage, both the pair of electrons will move along with, yes, CH3, and it leads to the formation of CH3 plus, yes, CH3 minus. Coming to the second example, the shared pair of electrons will move along with Cn, and it leads to the formation of a methyl cation plus Cn minus. In this case, CH3Cu, when the bond undergoes heterolytic cleavage, the shared pair of electron will move along with CH3, which leads to the formation of CH3 minus plus Cu plus. A chemical reaction may be considered as the rearrangement of electrons, and the movement of electrons is represented by curved arrows. And coming to the electron movements in organic reactions, the movement of electrons, as I have told you, is represented by curved arrows. Now let us take some of the examples of which shows the movement of electrons in organic reactions. First example, you have a double bond, which means that you have a pi electron, and if you can observe here, the movement of pi electrons has taken place to the adjacent bond position. Therefore, the double bond shifts from this position to the adjacent bond position, and there was a double bond here before the movement of electrons. Now after the movement of electrons, the double bond is shifted to the adjacent bond position. In this case, the movement of pi electrons takes place to the adjacent atom, and in the third case, the movement of electrons has taken place from the atom to the adjacent bond position. These are some of the examples to show how the electron movement takes place in any organic reaction. Electron displacement in a covalent bond. We all know that a chemical reaction is nothing but the redistribution of electrons, and the electron displacement in a covalent bond can take place in the ground state under the influence of an atom or a substituent group or in the presence of an attacking reagent. The electron displacement under the influence of an atom or a substituent group will cause a permanent polarizability in the molecule, and the inductive effect and the resonant effect are some example. Whenever the redistribution of electrons or the electron displacement takes place under the influence of an attacking reagent, then it causes a temporary polarization of the molecule, and electromeric effect is one such example. Inductive effect. Now let us assume that a covalent bond is formed between atoms of different electronegativity. We all know that electronegativity is the tendency of an atom in a molecule to attract the shared pair of electron towards itself. Thus, the electron density will be more towards the highly electronegative atom. Now, consider a molecule to which a highly electronegative atom is attached, as in this case you have a molecule to which a halogen atom is attached, and we all know that halogen atoms are highly electronegative. Due to the difference in electronegativity, the shared pair of electrons that lies between carbon and halogen is not exactly in between the two atoms, but will move slightly towards highly electronegative atom, that is halogens, and the halogen atom will develop a partial negative charge and the carbon atom will develop a partial positive charge, and the movement of electrons will be towards the highly electronegative atom, that is halogen, and it can be indicated by an arrow mark. Now this carbon has a partial positive charge, will attract the shared pair of electrons between these two carbons, and this carbon will again develop some charge which is indicated by delta plus plus, and what happens, there will be a polarity developed in the molecule, and this polarity goes on shifting along the carbon chain, and in this case the positive charge or the polarity developed on this carbon atom will be more when compared to the polarity developed on this carbon atom. That is, as the chain length grows, the polarity that is developed goes on decreasing, and this type of polarity induced in the carbon-carbon sigma bond due to the presence of a polar sigma bond is known as inductive effect. The inductive effect is dependent on the ability of substituents either to withdraw electrons or to donate electrons. That is, the substituent may be an electron withdrawing group or it may be an electron donating groups. Some of the examples for electron withdrawing groups are halogens, nitro, that is NO2, cyano, that is CN, carboxyl, that is C over H groups, esters, C over R, and aryl oxy groups like OCH3, O6, C6H5. Some of the electron donating groups are alkyl groups like a methyl group or an ethyl group.